purifying proteins. So prions are always of interest to people. They're always a little scary to people. It's probably prions that probably turn more people into vegetarians than anything else I know. Vegetables don't have this problem. So, okay. Well, I want to spend a little bit of time talking about how it is that we get proteins to work with. All right? That's useful to know. Many of you may go eventually and work in a laboratory, and one of the things you'll discover when you go to work in the laboratory is that proteins are probably the most common things that you try to isolate from cells. So it's worthwhile understanding a little bit about how we do that. I won't spend too much time on it, but I will spend a little bit of time talking about that. Okay. Well, I used to make my class go through and be able to do these calculations, and I decided you guys have enough calculations. We'll focus more on some specific things. The other thing I noted, and I put it in the highlights yesterday, was I used to make you calculate PI. You will not need to calculate PI. You may have seen it in the problems, calculate the PI of this. The PI is, you should know the definition of it, but you're not going to have to calculate it. And the definition of PI is the pH at which a molecule's charge is exactly 0. Underline the exactly part. PI is the pH at which a molecule's charge is exactly 0. I'm not going to make you calculate the PI because, to be honest, I don't think it's worth the effort that you put into learning how to do it. Okay. Well, why do I show you this table? I show you this table because it actually shows you several techniques that we can use for purification. So we're not going to worry about the calculations, but I am going to show you that there's different steps that we can take, different things that we can do, each step of which gives us our protein in a purer form. So let's think about this. If I take and I want to isolate a protein, I've got my factory that makes the protein, of course, are cells. So I want to get a protein. I want to get a lot of protein. I want to get a lot of cells. So I grow up a whole bunch of cells. All right? I might be getting a protein out of yeast, for example. So I can grow up, a lot of yeast. I can spin it down in a centrifuge so that all the cells go to the bottom, and I've got my cells there. And I'm going to bust these cells open. And when I bust these cells open, I not only have my protein, I've got 3,000 or 4,000 or maybe 6,000 other proteins there. All right? The reason I want to purify it is I want to study one protein. I don't want to study 6,000 at once. I don't know how to study 6,000 at once. So the techniques that I'm going to be describing then really allow us to get that one protein that we're after to the exclusion of others. Now I want to emphasize there's no one way to purify any given protein. The methods that we use depend upon the characteristics of the protein. They depend on the characteristics of the protein. Okay? Let's say my protein, when I take my protein and I spin it down, or spin the cells down, and I bust the cells open, I have really two groups of proteins that can be in there. One group is going to be able to dissolve in water, and one group is not going to be able to dissolve in water. So maybe I've gotten rid of half the proteins. If I just take the water, because it's going to have the ones that are dissolved in the water in them. I could then further take that water that has the dissolved proteins in it, and I can start treating it with salt. It turns out that when I start treating proteins dissolved in water with salt, some of them become less soluble. So you see I'm having ways now, I'm having steps, each of which is either going to precipitate or not precipitate or isolate or not isolate a group of proteins. So I'm going to continue these steps over and over until I eventually get my protein. Ion exchange chromatography is the first technique I'm going to tell you something about. And it's a very cool technique. Okay? Ion exchange chromatography relies on charge as a way of isolating something. Okay? I'm going to start right here at figure 5.7. I'll come back to the others. Okay? We've been talking about charge a lot. And the charge that we've been talking about, I said, well, the charge changes as the pH changes, right? Because the pH changes affect whether the proton is on or the proton is off. I can manipulate the charge of a protein by changing the pH of it and perhaps get it to have a charge that I want to help me to isolate it. How does that work? Well, the technique I'm going to describe to you is called ion exchange chromatography. And it uses a column. Okay? So imagine I've got a tube. And into this tube, I've got a whole bunch of little tiny beads. The little tiny beads have attached to them chemicals. So I have a bead that's a little round thing, almost maybe a millimeter in diameter, pretty small thing. All right? And attached to that bead are chemicals sticking out in all directions. And the chemicals that are attached have structures such that they are either negatively charged or they are positively charged. Right? So one group of beads may be negatively charged, another group of beads may be positively charged. Everybody envision that okay? So I can have a column over here that's got negatively charged beads, another column over here that's got positively charged beads. If I take my protein, I've got a mixture of proteins. Let's say I've got 100 proteins in my tube, and my protein at a given pH has a positive charge, and I want it to stick to the column. I'm going to use a column that has negative charges, and the negative charges are on what are called a cation exchange column. In a cation exchange column, the positively charged proteins are going to stick to the column, and anything that's not positively charged is going to come through it. So I take my proteins, I pour it on the top, the things start moving through the column, my proteins are sticking where they're positively charged, and maybe some other positively charged ones there as well, okay? But all the ones that are negatively charged or all the ones that are zero charge are going to come through. Does that make sense? Now, I've just done some separation. Because now I've separated the positively charged proteins from the negatively charged proteins. Make sense? Questions on that? Yes? How would I get those proteins back off of there? Well, let's think about this. It turns out that these negative charges didn't really start that way. They started that way with a sodium ion there, for example. So the sodium ion came off and the protein replaced it. If I want to get the protein off, I actually have to add a lot of sodium ions to replace the protein. So it's a good question. So I run everything through before I add more sodium ions. Then I add my sodium ions back. It replaces the protein. And now my protein and all the positively charged proteins come out. Make sense? Yes?
So the ones you want don't stick to the column.
So on the first round, so let's say I've got positively charged proteins that I want to get. So in the first round, I've got a cation exchange column. I pour this mixture on there. The first round, the negative and the zeros come through. I don't want them. Throw them down the drain. My protein is sticking to the column. So now I take and I add a bunch of sodium chloride in there. The sodium chloride releases my protein and it comes out. So ultimately, my protein will come out, but I control when it comes out. You might say, well, why do you have to do it that way? And the answer is you don't. Let's say I decided instead of having my protein stick, let's say I had all the other proteins stick. Maybe I wanted all the negatives to stick and my protein to come through. That'd be simple, right? I wouldn't use this column. I would use this one. Because now with this column, I've got positive charges there. All the negatives are going to stick, and my protein is going to come shooting through. So I can do it either way. I see some frowns. Yes? I would get the non-charged ones coming through as well. You're exactly right. Very good. I'd have to go through another round. That's right. And sometimes I have to do both of these. And it turns out that neither one of these is going to give me absolutely pure protein. It's just going to help me get rid of some things, but not all things. Okay? Does that make sense? Yeah. Lynette. I'm sorry?
The cation exchange
Will attract the positives. Yep. And the anion exchange columns will attract the negatives. Yes, sir? Can you adjust the pH? You absolutely can. And so that would be another way that you can get it to come off the column. Yep. Good, very good question. Okay, so that's one technique of isolating things. The methods that we use are typically called chromatography. And you might wonder why they're called chromatography. Oh, is your question?
So if you had more than one concentrator,
Yep. I'd have to do other things. So that's why I say I don't get this pure in this form, but I get rid of a lot of things that I don't want. Make sense? I'm going to get a whole bunch of positively charged proteins at this point. Okay. Chromatography chromatography literally is what the word we use for separation techniques. So I've described a separation technique that allowed me to separate the positives from the negatives. I earlier described separation between the soluble and the insoluble. Now I'm going to tell you another chromatography technique where we can separate big from small. And this one's pretty cool. This one's called gel filtration. You also hear it called gel exclusion chromatography. Now, this one actually has some very cool things that it uses. Okay? We use a column again. We use little tiny beads again. But now instead of having chemicals that are positively and negatively charged sticking out of them, the beads have a different property. And this property is pretty cool. And no, I don't know how they make these. I'd probably be rich if I did. But they make these little beads, and the little beads have tunnels in them. A tunnel. Okay? And the tunnel has a hole, and the hole is a set size for a given set of beads. So all the beads have the same size of holes, they have the same size of tunnels through them, and the tunnels go all kinds of squiggly directions through the bead. Can you picture that now? So we've got a little bead, it's got a tunnel, and it's going to and finally comes in here, comes out here. All the beads have the same size hole. Okay? Well, what does that mean? Well, let's imagine I've got a whole column of this stuff, and I've got my mixture of proteins. Let's say I had gone through, and now I've got all my positively charged proteins. Some of them are big, some of them are little. And let's say the protein that I want is big. Okay? A big protein, if a big globular protein is going to be like a big ball, a small globular protein is going to be a small ball. Okay? The small balls will be able to fit into these little tunnels, and the big balls will not be able to fit in. So if I pour this mixture up on top, what's going to happen? The analogy I like to give is you're going to a fair with a little kid. Okay? You're going with your parents and your own kid. So there's 3 generations here. Okay? The little kid, you get to the fair, and the little kid says, "Oh, Mommy, I want to ride here. I want to ride here." And Mommy says, "Okay, we can go right here." All right? Grandma and Grandpa go, "I don't think I really want to get on that ride. I'll lose my lunch." So instead of stopping at every ride, Grandma and Grandpa move through the fair fairly quickly. Grandma and Grandpa are the big molecules in the beads. Mom and Dad may go through 2 or 3 of these rides before they start losing their lunch, and they start saying, "Well, why don't you go? I'll just kind of watch you, okay, and make sure everything's okay." So Mom and Dad are starting to do this. They're sort of shuffling through. The last person through the fair is going to be the littlest one. The last one through this column is going to be the littlest protein, because they're going to every ride. And the ride in this case is the little tunnels. They take a longer path to get through the column than something that doesn't go in all those tunnels. It's a very cool technology. It's called gel filtration or gel exclusion chromatography. The 2 terms are equivalent. And they allow you to separate molecules on the basis of size. Yes? How would polarity affect it? It doesn't affect it at all. So polarity is not a factor. This separates only on the basis of size. Yes? Random. It's random. They're just so you got liquid flowing through, and so sometimes if they just happen to hit a tunnel, they go through it. It's totally random. Well, it's unlikely because you have so many thousands and millions of beads. The likelihood that they won't go through tunnels is very, very low. So in essence, what you see is essentially all the little ones do go through. Yes? Exactly. It bounces off. Exactly. Kind of cool. Yeah?
So to actually separate them, are you stopping, like, if you want the large molecules,
Yep.
you stop it quickly so you only have the large?
So it's quite a good question. How is it that I